And now the monthly view of the sky at night with Patrick Moore.
As you can see, I'm not in the studio. I am, in fact, at the University of Cambridge. This is a main astronomical centre, of course. Quite apart from the Institute of Astronomy, which has a very fine record, it's also the home of the Royal Greenwich Observatory, relocated here from Herstmonceux Castle in Sussex. There are telescopes here. For example, there's the Northumberland Equatorial, which has a very interesting historical record. This was the telescope used way back in 1846 to search for the planet Neptune. But there are no really large telescopes here. The Cambridge climate simply isn't suitable. Our main telescopes are either in La Palma in the Canary Islands or on the top of Mauna Kea in Hawaii. But all the same, there are not enough large telescopes to satisfy all astronomers, and that's why a new one's being planned. This is going to be a 4-metre telescope known as the Cambridge Telescope, or CCT for short. Why is it going to be called the Cambridge Telescope?
Well, it's a collaborative project between those of us here at Cambridge, the Institute of Astronomy in Cambridge in England, and the University of Harvard, which is in Cambridge, Massachusetts.
Where is it going to be set up? Not in Cambridge, presumably.
No, it's a little cloudy here. It's to go on a mountain called Cerro Pachon, which is in the Andes in Chile. The nearest mountain to that, which is presently an observatory, is Cerro Tololo, which is a large American observatory. And Cerro Pachon is also to be the site of the next joint British-American-Canadian 8-metre telescope, as well as several other large telescopes.
There are many larger telescopes in the world than the Cambridge telescope is going to be. After all, it's only a 4-metre or 158-inch. Therefore, why do you need this new telescope, and what is so special about it?
Well, the key word, as you note, is special, is that this is intended to be the only telescope which is deliberately designed around a capability to survey as large an area of the sky at one time as it can possibly do, and to take spectra of a very large number of objects at the same time. So all the other larger telescopes can study only tiny parts of the sky at any one time, whereas this telescope will be uniquely capable of studying some hundreds of times more area of sky at the same time as the new generation giant telescopes which are currently being built.
Why is that so important?
Partly it's because our understanding of astronomy is really very limited, and most of the really new discoveries in astronomy, astrophysics, have been made just by blundering upon things. So we've discovered quasars, we've discovered infrared astronomy, we've discovered X-ray astronomy, and no one had any idea they were there until we went to look. But now astrophysics has become reasonably advanced, and so it is possible to define what we want to know, what the really big uncertainties are.
What immediate results do you expect from the Cambridge telescope?
The point is that we know enough about the universe to know more or less about what we can see. We understand stars, we understand galaxies. But when we look at the universe to see what's really there, we discover that what we can see is not a very large part of what's really there. All the normal matter in the universe, the stuff that I'm made of, you're made of, is the tiny part of something else. We understand pretty well where the stuff that I'm made of came from, just the ashes of creation. But there's something else out there, and this other stuff, there's perhaps even 100 times as much of it as whatever it is that I'm made of. It's very similar to the question of what's really in a room. I look around this room and I see a chair, a table, and you think, fine, that's what's in a room. But that's not really what's in a room at all. This room is full. It's just full of something that you don't even notice when you look at it. It's not full of chair and table, it's full of air. And so what this room has really got in it is air. So when we look at a room and we see a chair and a table, we are like the way that astronomers look at the universe. Now, first of all, you need to know what to look at. To do that, you take pictures. And here we have a picture of the Andromeda Nebula, which illustrates what we are trying to achieve. This is a nice illustration of the difference between what one sees, the chair or table in the room, and what's really there, the air all around the outside. This curve here shows the speed at which stars are rotating, stars and gas are rotating about the centre of the Andromeda Nebula. The important point, as you can see, is that out here they're moving just as fast as they are in here, and yet all of the light is in here, What this curve means, way out here, is that there's just as much mass right out here as there is in here, and yet all of the light and all of the galaxy is in the middle. So if all of the galaxy is in the middle, what is causing the weight out here? That's the real puzzle. Something out here is more important than the stuff we can see. What is it? Well, we don't know. We want to know. And you can see the same thing again by looking at this comparison here between an optical picture of the centre of our galaxy, showing what our Milky Way looks like. Here's a picture of the galaxy as seen by COBE, the satellite that measured the microwave fluctuations. It also took an infrared picture of our galaxy. It looks totally different than it does there. If I took the entire mass of the Milky Way, the bit you can see, the shiny bit, and I squashed it flat, I would get a surface mass density in this thin layer of about 50 solar masses per square parsec. That's just a complicated set of units we use so that we look clever. What that means in real terms is 80 grams per square metre. Now that's a useful, convenient number, because the next time you go along to a photocopying machine or a laser printer or something like that, have a look at the end of the paper packet and it will say 80 GSM, 80 grams per square metre, same number. And that's amazing coincidence, but the mass of the Milky Way at the position of the Sun, if I were to squash the whole thing flat, is the same as the mass of one sheet of paper. And that's the lot, everything we can see. But the question is, what's really there? And there I get the answer, crudely, and we don't like to know it better, from looking at how fast the Sun goes round the centre of the galaxy, the same way that I use the mass of the Earth to get the length of the year and the speed of the Earth to get the mass of the Sun. So by looking at this 220 kilometres a second round the middle of the galaxy, I can work out what's really there, how much weight there is to stop the Sun flying off out of the Milky Way. And the answer there is 3 sheets of paper. So what's really there, the gravity, is 3 sheets of paper. What we can see, the Milky Way, is 1 sheet of paper. And the really interesting question is, what are the other 2 sheets of paper?
In this kind of research, how is the Cambridge telescope going to be of special help to you?
There are all sorts of questions that we don't know. We've got absolutely no clue what this stuff is. The only clue that we can get is by doing a similar sort of experiment in many different directions, in many different places. Now this experiment stressed the British National Telescope system to its absolute limits. I was intensely unpopular with the amount of effort it took to do that experiment, and that was the simplest, easiest one. To do this properly in many different directions is going to be an exceedingly laborious and time-consuming task, and uniquely requires a facility like the Cambridge telescope.
It's one thing to collect data, and quite another to study and analyse them. Data are no use if they're left lying fallow. One piece of equipment designed specially for this purpose is the APM, or Automated Plate Measuring Facility. And this should be particularly suited to work with the new telescope.
We're now fortunate that telescopes in Australia in particular and at Mount Palomar have surveyed essentially the entire sky with these glass sky surveys, which means we can now have an image of essentially any part of the sky in one of several colours. And the APM is a way of taking one of these glass plates, each will be about 12 times the width of the full moon on a side, scanning the plate and recording the information of perhaps 250,000 images on each of these fields.
How do you go about identifying the most interesting objects, those you particularly want to study?
The machine actually provides us with a computer listing, if you like, on a magnetic tape of every single image in the field, and along with the description of each image, there's information that will tell us about its brightness, its position, its shape, whether the object appears like a star, essentially unresolved, or perhaps is a galaxy.
We've heard a great deal about these strange things we call gravitational lenses. What exactly are they and how do they work?
Well, gravitational lenses, Patrick, are a very important way of trying to study dark matter. The idea comes out of Einstein's theory of general relativity, where the space-time is actually distorted by the presence of mass. And that means that if we think of light, photons, travelling towards us from a very distant source, then as the photons come close to a mass, it could be a star like the Sun, it could be a galaxy, it could be something exotic and completely different, then its path will actually be distorted.
The Cambridge telescope is going to have a very wide field of view. Why is that going to be such a tremendous advantage?
One of the most spectacular examples of gravitational lensing is that caused by the presence of a giant galaxy cluster, distorting the background images over a wide field of view. And there will be arcs and multiple images and little arclets. And the best way to study that distribution is to take spectra of many of the arcs and the multiple images all at the same time. And the new developments in fibre technology have enabled us to actually design the telescope to incorporate such instrumentation.
The Royal Greenwich Observatory has a complete fibre optics laboratory.
It's the same fibre optics as is used in cable television, cable telephones, computer connections these days. Here's some. It's a very thin piece of glass. You start off with a piece of glass and stretch it. If you do it slowly, it doesn't break. And then you just shine the light down the glass. Now that wouldn't help, of course, the light would come out through the side. So what you do is you put a thin layer of some other reflective material called cladding around the outside, and then the light simply keeps bouncing around backwards and forwards down the inside.
How does this method help you to collect the whole mass of information?
Well, the really key feature in this part of it is that to remember that the focal plane, the bottom part of a telescope, is big. And here, in fact, is a real item, a real part of the optical fibre routine, which in fact shows you how big the focal plane of a telescope is. But each of these little points corresponds to a faint galaxy that one would like to get a spectrum of. I'll show you how that works here. You can see as I move it around with the lamp behind it, each of those little holes corresponds to the place where there is a faint galaxy in the sky. So if I take this plate, plug it into the telescope, each of these little holes will then correspond to a place where there is a faint galaxy. Now what I can then do is take a set of fibres, and here's a real set of astronomical fibres, and I can take them one at a time and plug them into these little holes around here. And then the light will go from the telescope along these little fibres here and come out this end. And this is the other end of the fibre. You see here the fibres coming back again, and the light comes out there. And then you plug that into your spectrograph or camera or whatever it is, and the light will have come down the telescope, through the fibres, and out through here.
Obviously, you will use fibre optics together with CCDs, charge coupled devices.
That's true. There are two basic things we wish to do with the Cambridge telescope. One is to get spectra of a very large number of objects, faint quasars, faint galaxies, faint stars, whatever they are, through this mode. But also we wish to take pictures, images of very faint objects with superb resolution, and a large part of the motivation for going to Chile is the superb seeing. And the seeing is unpredictable, but when it happens it's too good to waste. So what we want to do is have a very high quality CCD camera sitting there all the time. When the seeing's perfect, the observer flicks in a mirror, and hey presto, you get an image.
Of course, the telescope won't be restricted to just a few programs, but it will be adapted to special needs. For example, we want to know more about the distribution of the galaxies in space, about which there have been very interesting revelations recently.
Well, let's look first at how they're distributed now, because that's the starting point. Here we have a picture of the whole sky, but it's sort of unwrapped into the two hemispheres, and this dark band running all the way around the sky is where we can't see the external galaxies, because our galaxy and the dust of the Milky Way is in the way. But if you look at the rest of the picture, there's a great band, bright band, where there are many of the nearby galaxies are situated, and a great clump in the middle, which is the Virgo cluster of galaxies. And this band is called the supergalactic plane. But this is just the distribution on the sky. Now, if we take a cut along here and look at the distribution of the galaxies in depth, then we see this diagram in which we see now we are at the middle, and this is distance away from us, measured through the redshift, and this is angle in the sky along this cut. And we see things like the Great Wall, discovered by Hooker and Geller, here, right across the northern sky, and there's another Great Wall in the southern sky, which is not as fully explored yet, and you can see that the galaxies at the edge here seem to die off. That's probably not real at all. It's merely the fact that those galaxies are getting too faint, and so one of the hopes is to extend all this picture a long way further with the Cambridge telescope.
What's the significance of the false colour diagram?
Well, now this is a representation of that, the density distribution of galaxies, and the red here is a place where the galaxies are particularly dense. We are at the middle, and depth is plotted outwards. This is the Perseus-Pisces chain over here. Over here is the Virgo and Hydra Centaurus association, which are a place where the galaxies are peculiarly dense. Blue is like the sea, the galaxies are absent there, and the yellow is the galaxies are slightly higher than average, but not much. The galaxies are not uniformly flowing like Hubble said they should. Now here we have a picture of the excess galaxy velocities. They are outwards if they're over here in red, they're inwards if they're over here in blue, and it's the other way on the other side, so things are going to the left in this diagram are reddish and things going to the right are bluish. Now if I superpose one on the other, we are in the middle of both diagrams and they're both on the same scale. And we can then try to see how they go together. And indeed, the outward motions, the outward excess motions of the galaxies on the near side of this great concentration are too fast for the Hubble flow, and the ones on the far side of this great concentration are somewhat too slow for the Hubble flow, showing that the galaxies inside here have pulled the other galaxies a bit and speeded them up or slowed them down, as the case may be. And this is a way, of course, of weighing how much gravity corresponds to how much light. It's far more than you would get for an individual galaxy, and it includes, of course, the dark matter that we can't see. And so this is a way of weighing how much total matter there is in the universe. There is still controversy about the numbers we get from this. Some people think it's enough to slow down the universe and even make it stop, and some people say, no, there's only about a third as much as do that, and the universe will go on expanding forever, and it's an open and infinite universe.
And finally, it's fair to say that the Cambridge telescope will be undertaking programs which no other telescope in the world is geared to do. What is the present state of play?
Well, Harvard have got most of the way to the $20 million that we think is necessary for funding this telescope. Cambridge is well behind, where something like 1% of what Harvard have got, and we very much want to try and catch up with them so that we can pay our full share and take the full half of this telescope. I think the two of us together have marvelously complementary interests in this subject, and we would work very well together, and there's been very good collaboration on the design of this telescope, in which we have really pushed them towards multi-object spectroscopy, in which the Anglo-Australian telescope led the way, and so our boys have a great advance there.
It's clear that there's going to be a great deal of work for the new telescope to do. It won't be among the world's largest, but it will be set up under ideal conditions, and more importantly, it'll carry out programs which simply can't be done anywhere else. At the moment, Cerro Pachon is merely another peak in the Atacama Desert of Chile. If all goes well, there'll soon be a major observatory there. I look forward to presenting a sky at night from Cerro Pachon. Meanwhile, let's hope it won't be long before the Cambridge telescope is turned toward the skies.